Okay, an old extension to HSC question. Let's have a look. The diagram shows a complex plane with origin O. P and Q represent arbitrary non-zero complex numbers Z and W respectively. Thus the length of PQ is the absolute value of Z minus W. Okay, so that's Z, that's W. And then if you did with vectors backward through Z, forward through W, this vector here to the right would be Z minus W. Okay, and therefore its length is going to be the length of Z minus W. So this vector would have a length of absolute Z, this vector would have a length of absolute W. Okay, copy the diagram into your writing booklet, use it to show, and then they've given you this identity here, which you should recognize as a sum of two side lengths being greater than or equal to the third side. So that gives you a good idea that we're going to be using, it looks like a version of the triangle inequality. Okay, so let's start off. So we're going to use the fact that the key idea of any triangle inequality is the sum of two side lengths in a triangle is greater than the length of the third. So applying that here, we can say therefore that absolute value of Z plus absolute value of W is greater than absolute value of Z minus W. And we should just talk about the equality case separately. Also, you could have POQ being a straight line. Nowhere did it say that they have to form a triangle. So also POQ could be a straight line. Could be straight. In this case, therefore we could have absolute value of Z plus absolute value of W equaling to absolute value of Z minus W. Okay. Combining, we'll call that 1 and 2. From 1 and 2, therefore absolute of Z plus absolute of W greater than or equal to absolute Z minus W. Okay, so that's the first part, using the triangle inequality or proving a triangle inequality with the two cases. Okay, part 2. Construct the point R representing Z plus W. What could be said about the quadrilateral? Well, if this is Z and this is W, by parallelogram law, I can form a parallelogram. And therefore the point, I'll put a dot for the point and I'll put R there. That represents Z plus W. What can be said about the quadrilateral? It is a parallelogram. Okay, by the parallelogram law. In the particular diagram, it looks like a rectangle, but nothing has told me that it is a rectangle, so I'm not going to make that assumption. Alright, let's keep reading. If the length of Z minus W equals to the length of Z plus W, so if the two diagonals are equal in length, what can be said about the complex number W over Z? Okay, so let's have a think. So if length of Z minus W equals length of Z plus W, diagonals are equal in length, Diagonals of parallelogram are equal in length. Okay, well, what parallelogram has diagonals that are equal in length? Yes, it is the rectangle. So therefore, OPRQ is a rectangle. So what can be said about the complex number W over Z? Well, let's have a think. If we're a rectangle, that's going to be a right angle. So we're rotating to get from P to Q, we're rotating anti-clockwise by 90 degrees. So therefore we can write W is equal to KIZ. Okay, this is, let's do a rotate pi on 2 anti-clockwise. And the K is an integer, a real number not equal to 0. Okay, and that represents the dilation going from Z to W. Okay, so therefore what can be said about Z over W? Well, it equals to Ki. Where K is a real number, so therefore what can be said about W over Z? It is purely imaginary. What can be said about the complex number is purely imaginary. And that's what they were after. I like that question. See you in the next video.